Audible? Thumbs up. I enable mic option. Hello, am I audible? Hello, am I audible?
No, sir, it's very low, your voice. Little bit audible.
Hello. Hello.
Yes, sir. It is audible now.
Hello, am I audible?
Yes, sir. You are completely audible.
Yeah, I think now the device is correct, so we can start the session in 5 minutes. You can
Okay.
put the questions in Q&A section. So I'll uh, review it while the session and can answer it along with it. So there is another Q&A option in which you can put your queries, which I can respond. If your pre-queries are there, you can put it there. So good afternoon to everyone. We'll start the session now, and the recorded session will be uploaded on my YouTube channel on a later date. And the nominal fees that has been kept for this session, I think the details are available now. uh, it is 3:45 and we should start the session now. So I just wanted to know from you how many have read the code IS18168, that is ductile detailing of steel structures. So you can let me know if you have read the code completely. And happy Republic Day to all, the 75th Republic Day. Hello. Yeah.
Good afternoon, sir.
Yeah, good afternoon, Ravi.
Sir, this is Ravi Teja. Actually, I have not gone through this code, sir. I joined the session to just with the more intention of a comparison for IS 800 and this code, sir. In terms of shear and bending moments, to what extent this code shall be more used? Will it this code will it survey the purpose of dead load and live load at the basic level? Or exclusively definitely should be followed for seismic only? In that aspect, can you put some points?
Okay, sure.
Hmm.
So, Vishal, have you gone through the code? So it will help me know that what depth I have to cover as per the uh, requirement. Umesh, have you gone through the code?
No, sir. I have. I have not gone through the code. Sorry.
Okay, okay, no problem. So let us go through the code. It is a 28-page code, and this code has been put out as replacement to section 12 of IS 800 2007. So section 12 that we were using previously from the IS 800 2007, this code has been separated out from that section 12. Okay, so we need to refer this now as a ductile detailing requirement for steel structures. That is the intention behind this code, and they have uh, marked it in the beginning in the forward section. So I will just present the code and we'll go through it clause by clause. I hope my screen is visible to all.
Yeah, it is visible, sir.
So it is a year 2003, just last year it has released, and the title is Earthquake Resistant Design and Detailing. So it is both design and detailing of steel buildings, code of practice. So buildings that are designed as per this standard are expected to sustain damage during strong earthquake ground shaking, and the provision of this standard are intended for earthquake resistant design of only regular type buildings in which there are no dampers or dissipation devices. To control loss of life and property, base isolation or other advanced technique may be adopted if required, for which the Part 6 base isolated buildings should be referred. 1893 Part 6 2022. And most importantly, the provisions for ductile design and detailing of steel structures were first published in the country as section 12 of IS 800-2007, but a need was felt for having a separate and detailed standard dealing only with earthquake resistant design requirements of steel buildings in line with 13920, that is for concrete. Okay, so towards this cause, NDMA offered financial assistance for research on the subject, which the committee and BIS code has now acknowledged. So the entire reason for development of this code has been mentioned here. So standard contains provisions specific to earthquake resistant design of steel buildings using moment resistant frame or the braced frame as your lateral load resisting system. Okay, so moment and braced lateral load resisting system are covered in this course, in this code. In particular, provisions related to mechanical properties of steel and welding electrodes, design of beams, columns, joints in SMRF, and design of brace, shear link, and joints in braced frames are covered. So all these aspects that are related to the spatial moment resisting frame and the braced frame are covered in this code, which were previously in section 12 of IS 800-2007. So that was found to be limited. That's why a separate code has been detailed out for this particular purpose. Thus, provisions of this standard shall govern when in conflict with those of section 12 of IS 800-2007. So these are the latest standard and latest clauses which should govern the old clauses that were released in 2007 in IS 800. So I hope the first part is clear why and where to use this particular code. So development of this standard effort have been made to coordinate with standard and practices across the globe. So assistance has been taken from AISC 360 and AISC 341. This is for specifications for structural steel buildings, and this is seismic provisions for structural steel buildings. AISC provisions have also been referred for development of this code. The composition of the committee is in action B. The purpose of deciding whether a particular. Okay. So now we will start with this standard. So again, design and detailing, both aspects are covered for structural components and members of steel buildings designed to resist the earthquake shaking so as to provide them adequate stiffness, strength and ductility to resist the severe earthquake shaking without collapse. So this line is same as IS 13920. Okay. In that also the same statement has been given, so it is repeated here. The provisions of this standard shall be adopted in the design of the following types of steel buildings located in seismic zone 3, 4 or 5 of IS 1893. So it is for zone 3, 4 and 5. Now we have zone 6 as per IS 1893 2023. So if the zone 6 is there, so this standard will be updated later on. So in high seismic zones, except 1 and 2, this code has to apply. Again, it is same as 13920 statement. So residential, educational, institutional, office, business buildings, community, lifeline, utility, all buildings, this standard has to comply. So optional for buildings in seismic zone 2. The provisions of this standard apply for design and detailing of steel buildings having the following structural systems: SMRF, spatial concentrically braced frame SCBF and eccentrically braced frame EBF in the steel building. So we are using three type of frames. One is a spatial moment resisting frame, and concentric brace frame and eccentric brace frame. So three frames are that we are using for LLRS, and for that the detailing and the design clauses have been given in this code. In seismic zone 5, all steel buildings shall be made of EBF. For zone 5, only eccentric brace frame is proposed. The reason is it is giving higher energy dissipation and the failure position is also better, and that is the reason eccentric braced frame has been suggested for seismic zone 5. How to design EBF? You need to refer a separate document, or you can say some research papers are there by our IIT professors. You can refer that and can understand better that what is the how the EBFs have to be designed exactly. So for zone 5 it is EBF system, and SCBF, that is concentric brace frame, should not be used. We can still use SMRF but not SCBF. In seismic zone 4 and 5, SMRFs may be used in buildings of height less than 15 meters, not more than 15 meters. So in zone 5, in zone 4, uh, for buildings more than 15 meter, you have to use eccentric braced frames only as per the requirements of this code. So for factory buildings, you can use moment resisting frame and you can use SCBF, your EBF. So SMRF and EBF is possible in seismic zone and 4 and 5, uh, as it is up to 15-meter height. If the factory shed is let's say 22-meter, then it will go against this code. So for just 7-meter increase in the height, your structural requirement or the framing system will change to eccentric braced frame as per this code. However, for 22-meter height or 30-meter height, we are not using EBF till now. We are mostly using the moment resisting frames only. So, and we are also using SCBF, concentric braced frames. So SCBF, when we are giving the braced base in our industrial shed, those braced base will come under SCBF as they are concentrically braced, and moment resisting frame in the other portal frames. So wherever the braced bay is there, we are following SCBF currently, and moment resisting frame. But as per the new code requirements, we cannot provide this. But still currently we have not implemented EBF system in our PEB buildings till now. So if the factory shed is there, we are not following, but when you are making the the non-industrial buildings, that is for residential or commercial purpose, you can implement this criteria as it is easier to do in that particular case rather than the factory sheds. So it will become difficult for factory sheds to implement this, but simpler in the buildings, other buildings. So all steel frames in a building need not resist the earthquake, including the lateral forces. So that is the brace frame is taking the lateral force, moment frame is taking the other forces. So that way you have to decide which frame will take the earthquake force and which frame will be taking the other forces. And based on that, you can decide your lateral force resisting system in the building. So designer shall identify judiciously select frames to resist together the vertical loads and at least 80% of the effect of the design earthquake lateral load and designate them as the lateral load resisting system. So this is critical that identify and select judiciously the frames to resist together the vertical force and 80% of the earthquake force. and designate them as LLRS system. So what do you understand by this? That together the vertical loads and at least 80% of the effect of the design lateral load, and designate them as LLRS resisting system. So why 80% of the earthquake force has come here? So we may not use 100% of the seismic force in some of the buildings. So in that case, 80% or at least 80% of the earthquake force should be taken by the lateral load resisting system along with the gravity loading. Then we can title them as LLRS. Otherwise, we cannot title that system as to be lateral load resisting system. So they have designed how we can title something as LLRS and we cannot title something as LLRS.
Sir, I think like it should have a little small amount of ductility. Like it is supposed to get yielded, so they might have considered 80% rather than 100%.
The criteria behind this has to be seen, because at 80% what happens, and at 100% what happens, because we never design for 80%, we always design for 100% force only. Now this 100% force is the design force that we are designed for. So whether it is 80% of the I assume it is a design force, but from where this clause has come and how it is justified, that needs to be seen, that why 80% only, why 90%, why not 90% or 70%, why only 80% it has been restricted to. So a frame that will take 80% of the earthquake force along with the gravity force will be defined as LLRS, because in some cases, as I told, that you cannot provide the bracing. Okay, so in that particular case, the forces may come but may not be resisted to full amount. So 80% it may be taking, and your other system may also be present. So all those system that takes minimum 80% all have to be categorized under LLRS. Now you cannot say like it is a dual system. Now 20% is taken by the frame and 80% by the shear wall. Then you have to define the frame also as a lateral load resisting system. Same in this particular case, to define it as a lateral load resisting system, you need some proportion. So that proportion has been defined, that 80% of the earthquake plus the gravity load when it is taking, then we will title them as to be lateral load resisting system. So all members will get yielded at the ultimate state. Okay. So whether they are LLRS or not, how will you decide? Okay, so that is a different case. Yielding is a separate case as compared to transfer of forces, and how many frames are going to participate in the lateral load resisting system. So based on that, I think it may have been derived, but its derivation is still to be evaluated, and from where this clause has come.
Excuse me, sir.
Yeah.
For the steel buildings in general, are the stiffness modifiers begin during modeling?
Why stiffness modifier? Stiffness modifier we give only when it is cracking.
Achha, okay.
There is no concrete here, no
Okay.
reinforcement here. So reinforcement also we only give modifiers because of the concrete cracking.
Okay.
Steel will yield and steel will fail. Same is here. Steel will yield and it will go to hardening stage, and then after it will reach its capacity before failure.
Yeah. Okay, sir.
So there are no modifiers. Now the modifiers may be due to the fire. Okay, so in fire case, you can give the modifier 50% or whatever the clause is there, you are following, not for earthquake. So modifiers do not come under steel design. So that's why IS 800 does not have the modifiers, not this code will have that modifiers. So that is limited only to concrete buildings. The other frame shall be designed to resist the effects imposed on them due to vertical loads and the deformation capability induced effects of the earthquake loading. So like I told, some columns are gravity columns, or we can say it is a dual system. In concrete buildings, same categorization you can see in the steel buildings, that the system that takes 80% of the earthquake force and vertical force all come under lateral load resisting system. Other than this, whatever the elements are there have to be designed for the gravity loads, and whatever the deformation due to the earthquake is, displacement due to earthquake is happening, r times that displacement should be taken by that system. So I hope I'm able to explain you that how to categorize the system, and whenever you are designing a building, you should understand this clause very perfectly. Then only you will be able to implement in a correct direction. Further moments shall not be transferred to designated Further moments shall not be transferred to designated LLRS system from frames spanning in perpendicular directions. So earthquake X, earthquake Y, two direction forces are there. So in X direction, Y direction moment should not get added. So the frames in the other direction, those moments should not get added to the frames for the earthquake force direction we are right now considering. So if we are considering the earthquake to be in X direction, the frames in X direction will take the earthquake force. Frames in the Y direction, whatever the moments are there, should not be added to the frames in the X direction. So moments shall not be transferred to designated LLRS from frames spanning in perpendicular directions. So two direction moments should not get added in whatever the designated LLRS system you have designed. So shear wall in X direction will not take the moment in Y direction. Same shear wall in Y direction will not take moment in X direction. Similarly, the moments that are coming in a steel building in a particular direction, the perpendicular direction moments should not get added into that. This is very difficult because you need to evaluate a frame and then check whether that so the stiffness has to regulate in two directions in such a way that moment transfer does not take place between the two perpendicular frames, and the connection also has to be in that manner only. So moment does not have to come, that doesn't mean that. So in concrete you don't have that liberty. Concrete is a rigid connection, but still you can regulate whether the moment will get transferred or not. So you will detail the connection in that particular manner that moment does not get transferred in the perpendicular direction frames. Consequences of failure of structural members that are not part of the LLRS shall also be considered in design. So other than LLRS members that take the gravity force, uh, their failure, how will it affect the stability of the system, should also be considered in the design. So now the terminology, I will not cover all terminology. You can go through the definitions. The definitions are very clear. Now capacity design, how we see in the concrete buildings like beam fail. So hinges get formed in the beam, not in the column. Then it gives a good failure mechanism, that is we call a beam mechanism. Similarly, in plastic analysis that we do for the steel frames, If the beams are failing, then it is a beam mechanism. Column is failing, then it is a column mechanism. If both are failing, then it is a combined mechanism. Okay, so how the frame is going to fail under the lateral forces, that is actually very critical for energy dissipation and ductility. What would be the capacity of the frame to take the lateral forces? It will be governed by this particular manner, and if the beams are failing before the columns, it will be a capacity based design approach and will have higher energy dissipation capability. So capacity design, the design steps beyond those in the basic design of non-yielding structural elements, member and connections, which consider the effects of inelasticity incurred in yielding members, resulting in overstrength based demands on the non-yielding structural elements. So basically, in some members, inelasticity will get developed. In other members, overstrength will get developed because they are not going in the inelastic zone, but they are going through that same displacement. So the design steps which consider the effects of inelasticity incurred in yielding members some are yielding now, resulting in overstrength based demands on the non-yielding structural elements. So how we are dealing between two elements, one is taking the earthquake forces that will yield, and other non-yielding members, how will they behave? When we are considering the two, the uh, capacity of the both, because the lateral force is very strong, so lateral force design members are strong, other are not very strong, so they will fail before the member fails, our main member fails. So that way our system will not work. The earthquake forces should fail the main system first, then only it should fall, rather than our central system being very strong and outer system being weak, and central will stand while the outer will fall down. So same way we have to check whether the inelasticity of our lateral load resisting system should not damage the other non-yielding elements that are present in the system. So check for both. So that is the capacity design aspect that this code is highlighting here. So yielding members, non-yielding members, both should survive in the earthquake, and non-yielding members should not get failure before the yielding members. So second aspect is capacity protected elements. So components or members designed to remain elastic using capacity design principles. When an adjacent component or member undergoes inelastic straining during earthquake. So this is what I was talking right now, that components of members designed to remain elastic using the capacity design principles. So capacity of the lateral load resisting system, that are the yielding system, that is capacity 1. Nearby elements that are to be protected from being non-elastic, those are elastic. Okay, their capacity should be higher. That way our capacity protection clause works as per this code. So collector elements that collect the forces between diaphragm and the vertical members. Concentrically braced frame, I think you there would not be a doubt in this particular definition. Spatially concentric braced frames, SCBF. CBF specifically designed and detailed to provide ductile behavior as per requirements specified in the standard would be termed as SCBF. Otherwise, it would be ordinary CBF, not ductile designed. Ductile design, then SCBF. A weld connecting two structural components which are part of the LLRS and at least one of which is expected to undergo inelastic straining following the yielding will be termed as demand critical weld. So which is going to fail, which is having more strain and about will be fail first. Okay, so that would be a demand critical weld. That is the title given here. We generally follow that weld check, but if we are terming it, there is a demand critical weld term given in this particular code. Eccentrically braced frame, a lateral load resisting system composed of interconnected beams and columns with inclined members or braces that have at least one end connected to a beam through a link with a defined eccentricity from another beam to brace connection, with or without the aid of horizontal diaphragms or floor bracing system, in which the system resists gravity and lateral force effects primarily by axial force in the braces and shear and flexural actions in the links. It is specially designed and detailed to provide ductile behavior as per the requirements specified in this standard. So, uh, so if this is a particular story and this is a bracing, so this is a concentrically braced frame, whether it is spatial or whatever the case, this is concentric braces following the center line. And when we are talking about the eccentric brace, they are saying at least one end should be on the beam and other can be concentric like this, or other also can be eccentric like this. Okay, so this is eccentricity in two directions, two top and bottom. This is eccentricity in one side. So at least on one side, if the connection is eccentric for the brace, here it will take force by axial action. Okay, so axial force it will resist. Also, it will resist the shear forces. Okay, so that way the eccentrically braced frame and concentrically braced frames are defined. And based on that, the lateral load resisting system will have a higher R factor. Your R factor will be governed by what system you are choosing. And in zone 5, you have to use eccentric braced frame uh, for any building that is more than 15 meters in height. And you cannot use SCBF in zone 5. So doubler plate, this is a new term that has been added. A plate provided parallel to web of the column and connected along its own perimeter to the web of the column and at some intermediate locations within itself when necessary. So it is like if this is my column, this is the column flanges, and there is a plate inside the web, okay, in which along the perimeter it is connected to the web of the column. So these are called the doubler plates. So at what places the doubler plates are required, so that depends on the detailing requirement, and based on that you can decide where doubler plate would be required in your building. Shearing and flexural action are taken by the links. So this eccentric brace frame takes the axial force as well as the shearing and the flexural forces. It is specially designed and detailed to provide ductile behavior. So joint panel zone is very critical design for steel buildings where the beam and column are framing into each other. At that particular position, the panel zone will get created, and high amount of the shear and flexure and torsion moments get concentrated. So due to the uh, what we can say that diagonal tension, this zone may get fail. Okay, so that has to be properly detailed for that earthquake forces as well as for the other forces that are coming onto the building. So this has to be specially detailed, like we are doing for the joint design in concrete. Same we are doing for joint panel zone in for steel. We need to evaluate what type of force getting there and provide panel zone additional stiffeners in that zones for resisting those forces. So what is a link? The segment of a beam that is located between the ends of the connection of two inclined braces in eccentric brace frame. So here you can say this much zone is a link. This is the link zone. Okay, so this link takes the shear and flexure, and this takes the axial force. Protected zone, new term, area of a member or connection element designed to undergo inelastic straining under design earthquake effects and is required to be devoid of additional attachments or discontinuities resulting from fabrication and erection procedures. So what is protected zone? Which are designed to undergo inelastic straining during the earthquake. So all those are called the protected zones. So in that no discontinuity is allowed. So it should be fabricated continuous, and no discontinuity should be there in that zones that are protected zones, so that the flow of forces happen correctly. I hope now up to this point it is clear, because we have dealt with the principle and philosophy, how we are going to design the special concentric brace frames, eccentric brace frames, and moment resisting frames. Many things will remain as it is, but to understand that how to implement all these things is very critical, which has been covered in this code in very short manner. You need to refer good publications or AISC code to understand it in more detail. So design and construction of steel building shall be governed by provisions of IS 800, like we do for 456. 800 is a standard code, except as modified by provisions of this standard for those members participating in LLRS. So for those members that are earthquake resistant lateral loads resisting system, the clauses of this standard will govern. Otherwise, IS 800 will govern. So what are the type of material that is to be used? That also has been mentioned here. So grade E250, 275, 300, 350. Now in that the grade B0 or C has been mentioned as per IS 2062. So you need to check the material that you are using is of this particular type only. Any other equivalent grade of steel satisfying the following. So now steel sections are this. Now what is the additional? Characteristic yield stress Fy of the structural steel sections and plates in which inelastic action is expected shall not exceed 350 MPa. So your yield stress in which the inelastic yielding is going to happen, that should not exceed 350 MPa. So Fy is limited to 350 MPa. Structural steel shall have minimum elongation of 22%, like it is 14% for uh, concrete buildings. Now this is 14.5%, this is 22% for steel buildings. So elongation of 22% has to be maintained. Structural steel shall have minimum Charpy V notch impact test value of 27 joules at 0 degree Celsius. So this test has to be confirmed for other materials than the structural steel plates. The ratio of the ultimate strength to the yield strength shall be at least 1.15. Ultimate to yield strength, the ratio should be minimum 1.15. So when we are going towards higher grade, this is a critical requirement. So important is material uncertainty factors Ry and Ru at yield limit, at ultimate limit. Okay, so what is expected, what versus what is available, there will be some difference. Okay, so that ratio of the material uncertainty factor you have to consider while designing. So expected yield strength and expected tensile stress of a grade of steel shall be considered to be equal to Fy into Ry, Fy Fu into Ry respectively. So this factor you are adding to Fy and Fu for uncertainty of your material. So for different grades, the values are given in table 1. Any other steel satisfying 5.2b, that is 5.2b. Okay, values of 1.4 and 1.2 shall be considered for Ry and Ru respectively for such steel. So other than structural steel, 1.4, 1.2 is given. For structural steel, you need to find Ry and Ru from the table. So for 250, 275, 300, 350, Ry 1.2, 1.1, we generally use 350 right now. So in that particular case, 1.2 and 1.1 will govern the uncertainty factor. So your Fy is 1.2 times of that, Fu 1.1 times of that. So the filler material for weld shall conform to elongation of 20% and Charpy V notch impact value of 47 joule at 0 degree Celsius. So 20% for filler material, elongation should be there. All demand critical welds shall have Charpy V notch impact value of at least 27 joules at minus 20 degree Celsius. So 47 at 0, 27 joules at minus 20 degree Celsius. So this is for Charpy V notch impact value for demand critical welds. Bolts, nuts and washers shall conform to relevant Indian standard that have been given here. Very important is section classification. Structural sections of lateral load resisting system shall comply with the width to thickness requirements specified in table 2. So we'll go to that after this. Now, the general requirements for ductile design and detailing of steel building shall ensure that required capacity is provided to cater to the imposed demand. So, capacity for the demand in terms of stability, stiffness, strength, deformability and ductility. So all four criteria, robustness, okay, all those aspects that have been given in 13920, same have been mentioned here in this particular code. And stability, stiffness, strength, deformability and ductility are important criteria. Hence, the words capacity and demand refer to all the aspects specified above. The steel building designed in detail as per the standard are expected to resist the design earthquake hazard defined in IS 1893 Part 1 without collapse. So, no collapse should happen for buildings designed with this particular code. Okay, so this is uh, the real purpose of providing the ductile detailing in steel buildings or the concrete buildings, is to restrict the collapse of the building and give time for the occupants to go out, evacuate the building and be safe, and after which the building can fall and you can reoccupy after undergoing a thorough inspection. Now loads and load combination. Design earthquake load shall be estimated and combined as per IS 1893 Part 1 along with those in Table 4 of IS 800. In addition to those load combinations, the following load combination shall be considered for design of A. The columns in SMRF, columns in SCBF and columns in EBF. Then beams in SCBF and EBF. So columns in all frames, beams in brace frames only, braces in eccentrically braced frame, and D, all connections which are part of structural system in steel buildings. So all the connections as well as braces in EBF, columns in all frames, beams in braced frame should have this particular load combination: 1.2 dead load plus gamma LL live load plus or minus earthquake load M. Then 0.9 dead load plus or minus earthquake load M. Now earthquake load M is the estimated maximum equivalent earthquake force induced in the structure. So that is overstrength factor into earthquake load. Now this overstrength factor is also given here: 2.5 for SCBF, 3 for EBF. So we are having the capacity is 3 times, okay, that we are providing for the failure. So what we are providing the steel, it can take 3 times more the force. That's why it is a overstrength factor of 3 and 2.5 for SCBF. So 3 times the earthquake force you have to consider. So this becomes 3 times the earthquake force for EBF, 2.5 for SCBF. Similarly, here your factor is 1, but here you can see it is 3 times and 2.5 times. So apart from the load combination, this special 2 load combinations have to be added for steel buildings for the given cases design. Now gamma LL is the partial safety factor for live load. So it is 0.25 for up to 3 kN meter square, 0.5 for more than 3 kN per meter square. So it is 0.2, that is the part live load that we consider for seismic weight calculation. Same criteria applied here. Now imposed load as per part 2. So this is dead load as per part 1. So special load combination to be considered. 3D analysis to be considered. Stability: under the action of the design loads, the building and its components shall be stable and overall force and moment equilibrium shall be satisfied. Thus, the building shall not slide or overturn under the action of the design load specified in 5.5. So 5.5 is your load and load combination. The building shall not slide or overturn under the action of the design load, special design load case that is specified in 5.5. It should not overturn or slide. Now stability bracing requirement for members when required for structural system defined in 12 Stability bracing shall be provided as specified to restrain flexure or lateral torsional buckling of steel components or members subject to axial compression, bending moment or shear. So to restrain the flexural or the lateral torsional buckling of steel components or members that are subjected to what? Axial force, bending moment and shear force. So lateral torsional buckling and flexural failure should not happen, for which we are providing the stability bracing. So you need to check where the like flange braces we provide in the PEB buildings, that is to avoid the lateral torsional buckling of the rafters and top flange of the rafters. So that way you need to check where the stability bracing needs to be provided, so that the lateral torsional buckling as well as the flexural failure does not take place. The strength of the bracing connection shall be at least 1.5 times the corresponding strength of the bracing. So capacity factor given as 1.5, what we have 1.4 in 13920, it is been given as 1.5 for the bracing connection. The capacity of bracing multiplied by 1.5 times. So this is interesting. Same table we have seen. Just a second. So same table we have seen in IS 800 2007, okay, in which we have the A, B and C category, okay, for different type of members. Same has been made for limiting. So section classification is very critical. Now that has been included in 2007 code 800 as well as in this code, both need to be followed. For lateral load resisting members, you need to follow this table. Now limiting width to thickness ratio for compression elements. Now compression element may be bracing or it may be column of earthquake load resisting structure. So limiting width to thickness ratio for compression elements. Okay, so if it is a beam, then section type doubly symmetric rolled I section. So outstanding flange width to thickness. So flange width to thickness ratio 9 epsilon upon root of Ry. Web depth to thickness ratio 44.5 epsilon upon root of Ry. So depth of the web is and depth of the your thickness of the web and thickness of the flange should be governed by these two criteria for doubly symmetric rolled I section beam. Doubly symmetric built up I sections. So top and bottom are same flange, that is doubly symmetric. All both sides it is the same properties. So it is whether a built up section, whether it is a rolled I section, you need to follow this particular requirement. Okay. Now for column, doubly symmetric rolled, doubly symmetric built up I. Again, your flange thickness is governed by this. Your web thickness is governed by this particular formula in which Ca is less than uh, equal to 0.118 and Ca greater than 0.118. You need to follow this formula for thickness of the flange, thickness of the web. And for bracing, rolled or built up I section, box section, okay, then it is what we say that there is no outstanding flange to thickness ratio, but in all cases whatever the thickness are there, your formula will be the same for box section. So 21.4 epsilon upon root of Ry will remain the same. Flange width is the flange width minus thickness of the webs. Okay, so on the top side, if you consider the flange, then apart from the thicknesses, whatever the width is available in between, that you will take as a width. and vertical will act as a web. Okay, vertical web, horizontal your flange, and minus the thickness of the web, whatever left in the width of the box section, that will be taken as a width. So width thickness here, flange thickness here. Now it is links. So link, as I told, the beam between the two end portion of the bracing. Now doubly symmetric rolled or built up section, closed box section. So for web, so for your flange and for your web, the formula is given. For box section, for the flanges, it is 21.4 epsilon upon root y, which is same as above. But for this particular box section, it is 49.4 epsilon upon root of ry. So in the link section, your web thickness has to be higher and your flange thickness can be smaller for link elements. But for brace element, it can be same for box section. Now Ca is equals to Pu upon Py upon gamma m0. So this is the material factor that we already use. Py, yield force and ultimate axial force. So that is what you get. Ca epsilon is 250 upon Fy, the whole root. So I hope this table is you may have referred it previously, and you need to follow this rigorously right now. So there is one just hold on. So there is one article written by Dr. N. Subramaniam on this particular aspect of local buckling width to thickness limits in IS 18168 2023. So on page number 13. So here you can it is downloadable from the website of ISSE. Okay, Indian Structural Institute. Okay, from that you can download it. But if we go to it, okay, so here you can see structural steel design. Let us see, go to the conclusion for right now. So all type of sections have been mentioned here. So classification of section as per ductility, yes, compared with AISC code. Okay, so here it is 9, here it is 8.5 in AISC, here it is 44.5, it is 72, 1 minus CA root of 2.3 upon root of RY. So how 341 and 18168 are there, so both factors are compared, and more or less you might not get a lot of a difference. Minor differences you will get in this particular case. So major differences in this particular formula that you can see for box section in the links, it is very high, double than required as per AISC. So cross section width to thickness limits are a long-standing and reliable means to ensure behavioral objectives related to local buckling performance of structural steel members. Establishing the underlying assumption inherent in the current width to thickness limits developed over the course of last 80 plus years is critical to structural steel design using new steels and configurations. Existing width to thickness ratio given in the two codes suggests that each limit is unique to each element and loading, while actual limits are based on a small number of targeted non-dimensional plate slenderness checks. So for the full section, what would be the response? We are not exactly understanding. Seismic width to thickness limits provided by the two codes are not only to achieve the required strength, but also to ensure ductility and avoid premature fracture in the variety of different seismic force resisting systems. These width to thickness ratios include Ry, which is the ratio of the expected yield stress to the characteristic yield stress and depends upon the grade of steel. The limiting width to thickness ratios given in AISC and IS are compared, and it is found that values given in AISC are slightly different, especially for the web sections. A summary of the application of these width to thickness limits and their intended objectives is provided. Although AISC code allows either moderately ductile members or highly ductile members, IS seems to allow only highly ductile members. So there is no intermediate ductility available. We are only aiming towards highly ductile members, and the purpose of Ry is to derive these values based on the grade of steel. So this is one paper shared. You can also refer this, cross referencing with other codes you can see, and try to gain more insight in what has been suggested in the code, and what is the international norms. So deflection limit as per IS 800. So based on that, stiffness needs to be provided. Drift, the story drift for SMRF shall be estimated considering stiffness of the finite size beam column joints. In absence of rigorous analysis, centerline dimension of member shall be used to estimate the story drift. For braced frames, centerline dimension of member shall be used. So uh, that is criteria is not mentioned, but you need to check the drift. Now P delta effect has been mentioned. So whether it is a sway frame or not, Wi delta I upon Hi into Fi. Wi is the gravity, Hi is the horizontal force, Fi is the horizontal force, and Hi is the height, and delta I is your horizontal displacement. Same formula has been mentioned, but I think some things are missing here. But it is the same as formula given in IS 456 for sway frame and non-sway frame. So P delta effect to consider or not, it is based on sway frame or non-sway frame, but all frames that take the literal force are sway frames. So you will have to consider P delta effect in that. A value of alpha e greater than 0.1 is not permitted. So that is a very highly slender frame if the alpha is greater than 0.1. So that is not permitted. Strength as per IS 800. Capacity design we need to follow. The ratio of maximum unbraced length of the compression flange of a beam to the radius of gyration shall be about the weaker axis of the beam cross section shall not exceed 25 for a distance of 2 times the dB from the end of the beam to column connection. So LPR upon RY for the remaining portion of the beam shall not exceed 0.1. So slenderness of the beam section needs to be of the compression flange needs to be addressed, and the parameter given here should be followed. And for up to length of 2 times the dB, it has to be not exceeding 25. For beyond length, you can keep the unbraced length upon Ry to this particular limit. The stiffness of the bracing shall be as given below. Beam shall be restrained against rotation about the longitudinal axis at support and at intermediate locations along the length of the beam through the use of internal panel bracing without any external rigid support. So the rotation of the beam should be restricted by the bracing. So that should be the stiffness of the bracing. Lateral bracing shall be attached at or near the compression flange of the beam. So wherever there is a compression flange, you need to attach your bracing at that particular location so that it takes the axial forces. The lateral bracing shall be attached at or near both flanges near the point of inflection in beams. Okay, wherever there is an inflection point, that is your bending moment is 0. Okay, so at that point you have to put your bracing connected with that particular point on both sides, top and bottom, so that the axial forces come into your bracing and your bracing takes those effectively. So where there is a double curvature in the bending, okay, so in that particular case, wherever the inflection point is there, you have to provide the bracing at that particular point at both flanges. Now stiffness of the bracing. The stiffness of the bracing shall be as below. The shear stiffness of the panel bracing, the system closest to the inflection point in a beam bending in double curvature, shall be 10 Ry mpb upon lbr into df. Lbr is the unbraced length, df is the distance between centroid of the flanges of the beam. And this mpb we have to refer above, that is basically a moment, and based on that moment we have to find the stiffness. It should be greater than that, whatever you are providing. The shear stiffness of the panel bracing system other than near the inflection point in a beam and bending under double curvature, for inflection point it is 10, for other it is 5. So stiffness becomes directly half, requirement becomes half for bracing that is near to the inflection point and other than the inflection point. Now strength of the bracing shall be based on mpb again, df ry 0.025. Special bracing at plastic hinge locations. Now this was shear strength of the panel bracing. Now this is special bracing at plastic hinge locations. Shall be located adjacent to the expected plastic hinge locations. Both flanges of the beam shall be laterally braced. The axial strength of such lateral bracing shall be this much. So this was related to shear force. This is related to axial force. So both capacity has to be given to your bracing at plastic hinge locations, at the shear locations. So now the strength that you can refer. If you have any query, you can let me know. Now further design of each flange splice plate shall be at least 1.2 Ry Fy into AF. AF is the area of the flange being spliced. So right now we were into the beams. Now this is into columns. So as you know, we have already crossed 1.5 hours in the lecture. So should I continue or should we take it in the next session? In which you can also refer further and we can have a discussion in that particular case.
Sir, next session.
Yeah. So I also feel that it would be too much to address at a time. So you can go through the rest of the code and try to compare also that what were we doing till now and what difference is expected from us as structural engineers while designing the steel buildings. So that is very critical. That is what I wanted to address today as well. So thank you for joining, and you can address your questions in the next session. So that next session, uh, it may be on Sunday. at the same time or maybe another day. So I'll just let you know for the next session, so you can just refer the code till that point. Thank you for joining.
Okay. Thank you, sir. Thank you very much.
Thank you,
Yeah,
sir.
thank you.